Okay?
Yep, great.
All right, so a little bit about interpolation, because when you go to any GIS package and you have sample data points, it's going to ask you to do something. And so I just wanted to give you a feeling for the two most common defaulted interpolation methods. One is inverse distance and one is using kriging. And this is the formula for the inverse distance, and you can review that on your own. But what it's really saying is that the directly estimated value, which is the Z star over on the left side, is related to a mathematical formula based on the distance that is away from its neighbors to a power. And the P is the power that the programs will ask you, the surfer or you or whatever. Most people default to an inverse distance square. I find that most useful, but you can put any number in there, 1, 3, 4. Once you get up to inverse distance to the fourth power, you have squares there, so I hate it. But the inverse distance square isn't too bad. The only thing that is a little annoying is that oftentimes when you have a value or two in the field that are exceptionally high or exceptionally low, the inverse distance tends to just make a circle around that. So you got these little circles from time to time. So that's why that is. It's just there isn't any way around it with inverse distance. The other, it's not my favorite, but it is my favorite if we have not as many points as we need for kriging. There's no estimate of error, so you never know if you're really doing a good job or not. You really don't know if the values are really spatially related. Most of the values that we get off a field do have a spatial relationship, but there are some fields that do not. They're just random, and so just one composite test for the whole field would be enough. So you don't know any of that stuff, which is inverse distance, but it's very quick, it's very easy to understand. Very easy to write the program unless there's one embedded in your system. You don't need to know anything else. You just click the button and there it goes. So that's inverse distance. And it's most appropriate if your sample data set is less than 30. You know, if you're sampling densely or if you have a lot of figures, then kriging would be better. So kriging is a geostatistical process, and it gives you some idea of error at the end, and you can look at the variogram, which is the variation in your measured values with distance, and look at it and say, oh, that has spatial structure, or no, it doesn't have any spatial structure, which is something you can't do with inverse distance. So what it is, this formula over on the left-hand side, this little figure here with the star, that's the variogram. And this is a semi-variogram, actually, because it's one over the number of observations. And then these values here are the value at a certain point, and the difference between it and the value some distance h away. So again, it's the statistics, but it's relating the values within the field to the values of the neighbors. So most of the GIS programs you have, including ArcView, are going to default to something, and that something might not be appropriate. The best way to handle the data is to determine the semi-variance yourself. And there's a number of different programs, or if you're a computer guru and understand a little programming, you could do your own. I use GS Plus. Others use other things. I don't really care what you use, but to develop a variogram, I think, and to get the correct values for the range and the nugget and the sill, I think, are really important, because the rest of the geostatistical package, the kriging operation, uses that variogram in order to estimate the weights that estimate the interpolated points between your sample data. So if you have a really horrible variogram, you're going to have a real horrible estimate. This is what I'm talking about. The distance here, this is a relationship of the variogram to distance. You have the distance. This point A is the point where it kind of levels out. Up here in top, this is the sill. This is the range, which is the point that drops down here. So this distance here is the range. And this distance where it crosses Often it doesn't cross at 0, 0. It crosses someplace up in here. So this here is the nugget variance. This came from the gold mining industry, and so it is a relic from the gold mining industry. So the nugget is kind of the part of the variogram that the variogram model does not explain. There's a question here, semi-variance, what is it?
Yep.
If you've ever heard of a covariance, covariance is a variance of something that's also related to something that you're working with. So if you're working with, let's say, yield and phosphate out in the field, and you assume that there's no spatial difference, and you're putting treatments out there, you may find that there's no difference, but it really looks like there's a difference out there. And so what we do is research a lot of times. If we know that something else is varying in the field as well as our treatments, we'll take the variation of that other non-applied variation out of that. Like if you had a study on top of an area that was salty, we would compare the variation in yield with salt with the variation of the yield with our phosphate treatment, perhaps. What this is doing is it's taking out the variation due to space. So it's actually the inverse of a covariance. So that's what it is, a statistical term. But the semivariance is important because the rest of the geostatistical equations use that to develop the weights for the final estimates. And so that's what all this is. So the variogram is used by the programs that are embedded in ArcView and embedded in your other GIS programs to produce the statistical weights that are used to make the estimates. So again, if you don't have a good variogram, you're in trouble. If you want to know more about this, there's some stuff online. You just Google semivariance and you can get more mathematics than you've ever had to work with for a long time. So feel free. I use the book as a reference. It's the Applied Geostatistics, Introduction to Applied Geostatistics by Isaacs and Srivastava. It's been out for about 10, 15 years, something like that, Oxford Press. It explains things in very simple terms, and because of the time, I couldn't go into detail. But if you come to NDSU and take our Precision Ag course, I can lead you through an exercise.
What is the name of the book? I'm sorry, so we can share it?
Yeah, it's an Introduction to Applied Geostatistics.
Okay.
It's by Isaacs and Srivastava.
Okay,
I will spell that for you later.
Yes, we'll include it as reference material.
Okay, good. All right, so here's some layering suggestions as I get close to wrapping this up. There's a couple things to look for. One is some programs aren't very picky about boundaries. You can measure boundaries a different way and layer something else that was measured another way, and it doesn't care. I think ArcView is pretty forgiving. But if you use anything that has Surfer embedded in it, Surfer is really picky about having exactly the same boundaries for things that you layer. So just check it out and make sure that the program you're using is going to be useful for you, and that'll help you collect your data and make sure that when you start to layer, that you don't have to go back to the beginning, which is a real annoyance and a waste of time. And so these are some other things I found very useful, and that's to normalize all your data. And the reason why is that when it comes in and starts chewing on this data and putting layers on top of each other, it's going to look for the same ranges. A lot of our imaging ranges from 0 to 256, whether it's black and white or color. So you would normalize it from, say, 0 to 1, 1 to 100. Yields might range from 0 to 300, or if you have sunflower in pounds, it'll be 2,000–3,000 pounds maybe. So divide by your highest yield to normalize your data from 1 to 0 to 1 or 1 to 100, and EC as well. You could get ranges from 0 to even over 10. And so you can see that the range of each of those types of data is different, so you want to make sure that they're all the same. Another thing to keep in mind, and this is advanced training, I guess, so when you start to put things into those kind of categories, think about we're talking about EC, high is bad, low is good, but yields high is good and low is bad, and imagery high is usually good and low is bad. So you might want to even think about inverses, perhaps, in order to make things a little bit more, because the computer is not going to know what those numbers mean, but the final numbers mean a lot to you. So if you want to cluster things into highly productive zones or least productive zones, you might think about how that data relates to that, and you might have to take some things and do the opposite of it. See what I mean? Instead of 0 to 10 EC, you might think about having the 10s actually be the zeros and having the zeros actually be the 10s. So you might want to inverse it in order to get things in the same scale. So these are the kind of maps that you get when you're layering things. You'll do the same thing if you're layering different years of imagery data, for example. This is using a hydrology model, the hydrology toolbox within ArcView, satellite image, slope gradients over here. The hydrology and the satellite image really pick out this fuel and soil over on the left-hand side. So some of these things are more useful than others. Playing around with them and trying to get what's best for your area is probably the best way to do it. This is that beach that we did before, and this is using two different models. This is beach, but elevation using hydrology in the satellite. So the zones are kind of clustered together, and I think you can make an argument for maybe that's not a bad thing. And here's the EC model with that. And it's really identifying those areas that have the salt issues where this one, which is hydrology in the satellite, doesn't.